Just as an outline of what I'm going to talk about in the next 25 minutes or so, you've heard a lot about vortex shedding from the various keynote speakers, and in particular in the Shanghai Tower session yesterday. And I was going to just get a little bit more detailed in the discussion and maybe relate it to some things that we observe in nature, and talk a little bit about its importance for supertall buildings and important in specific megatall buildings. Some examples I'm going to show from China, following the CTBUH definition of megatall being greater in height than 600 meters. The second topic will be applied meteorology, and specifically its application in wind engineering. And for those of you who don't interact with wind engineers a lot, it is something that's embedded in our work and maybe not quite so visible in the end product. But there are some things that, and some new techniques that we have available that I'll discuss a little bit, and how we've applied those to some very, very tall buildings. And then finally, although it's not my area of expertise, I'll just comment briefly on natural ventilation and some of the potential that we have now for some further detailed analysis with some building-specific data, both from the wind tunnel and some of the meteorological tools that I'll mention. So the first topic, vortex shedding. And vortex shedding is something that gets talked about a lot in the context of tall buildings, but I just wanted to assure you that it is very much a real thing. And this is a great image, satellite image, of vortex shedding is visualized in clouds as wind flows past a mountain in Chile. And so if we sort of put some schematics on that to understand what's happening, and imagine a building in the place of the mountain, then say we have a simple building shaped a square, and the wind is flowing more or less from left to right in this picture, then we see that these vortices form. So the vortices form in these circular patterns, and really, as far as the building is concerned, it's the formation of those vortices in the immediate wake of the building that matters. And it's the formation of those vortices that creates an alternating side force. So we have a side force that goes back and forth and affects the building, and if the conditions are right, the building will vibrate in resonance. And obviously, for those of you that understand what resonance is, it's not a good thing. So if we look at just a very simple equation, apologize for including an equation, but if we look at a simple equation up here on the left, that characterizes vortex shedding pretty simply. And it relates the frequency of the shedding to a few key parameters, or one key non-dimensional parameter, which is called a Struve number, and that's a dependent or a shape-dependent parameter. And then it also relates it to the velocity and some crosswind dimension. And as I say, it's a shape-dependent parameter, so that's something that implies that we have some control over it. Well, we do have some control over it to some extent, but as we get taller and taller in our buildings, then other things start to bring vortex shedding more into the design range, and it's just something that we can't really avoid, at least not practically avoid. So if we have a particularly tall building, then that means that the natural frequency gets shorter, and we see that it's proportional velocity. So that brings the velocity at which we get so-called resonance, when the shedding matches up with the natural frequency, into the design range, and that's just a practical thing that we need to deal with. But as I say, we do have some control over shape. So I've heard it mentioned a lot that a circle is bad and a square is good when it comes to vortex shedding. And for typical height buildings, just throwing out a height of, say, about 200 meters, that's generally true. But for the taller buildings, again, because the frequency gets shorter or the period gets longer, then that may not necessarily be true. So we see that a circle has a much higher rate of vortex shedding, or vortex shedding, in the wake. You can see that there. So it's about a 40% higher. Now, what's sort of counteracting that, or counteracting one's intuition of circle good, square bad, or sorry, circle bad, square good, is that the force associated with vortex shedding increases with velocity squared. So if you increase the velocity at which the lock-in occurs, then you're going to get a much higher force. So again, I just give a very complicated explanation there for a simple equation just to convey that it is a little bit more complicated than meets the eye. But it is something that we can control, something that we can have some design options over, and as Adrian Smith in particular mentioned in his keynote yesterday, some of the things that he and his firm consider very early on in design. In the neighboring session, there's a presentation going on about Ping An Financial Center, and that's one that we were working with KPF, Thornton Tomasetti, and locally here, CTBUH. And that's a building that took as a sort of a model some of the things that we've learned about reentrant corners. So if you look at the building, if you look at the building, it has some corner detail, and from the rendering you can see that corner detail changes over the height of the building. So towards the bottom it has a detail like that, and then as it gets towards the top, it not only gets smaller in cross dimension, but that detail of the reentrant corner changes. So in effect, they're changing the Struve-Hall number relationship over the height of the building, therefore reducing the correlation of the vortex shedding. A specific example that Adrian mentioned yesterday. Let me try this instead. Okay. A specific example that Adrian mentioned yesterday was the Wuhan Tower that we were privileged to work on with them. And in that case, we worked on a few different configurations. Adrian mentioned the corner detail that was trying to sort of direct the flow around there and affect that vortex formation. And so we investigated that as a sort of a sole solution, and then looked at some variations in that, and then finally arrived on a solution that, as displayed in Adrian's presentation yesterday, that had the open top. There we are. The open top, but also some venting as it went down the building, in addition to that sort of cornering detail. And then finally, here in Shanghai, we worked on the Shanghai Tower. Again, the design team mentioned there, and again, Sir Thornton Tomasetti and locally Caddy. And if you were in the Shanghai Tower session yesterday, they mentioned the sort of battery of tests that we put this tower through, and the different configurations and the different angles of twist going up the building. So there was a 100-degree configuration, 120, which is the version that's under construction. But what we found is that this version with 180 degrees twist actually performed the best, with about an additional 10% reduction in load. But it's always a balance of architecture and client wish. And from a visual perspective, this was deemed not as attractive as the 120 degrees. So in addition to looking at that, because the tower had rounded corners, we were concerned about the effect of Reynolds number. Reynolds number is a parameter I won't define in too much detail here, but just to say that the force coefficient changes with Reynolds number. So it's a parameter that we wanted to look at a little bit more closely, and went to a large-scale model in the 9-meter by 9-meter tunnel in Ottawa. And obviously, a significant large scale. These are not small people. And what we found is that at the higher Reynolds number, in fact, the force coefficient did change. And it changed towards the top of the tower, not as much towards the bottom of the tower, where the turbulence induced both by the ground and also the surrounding buildings took away some of that Reynolds number dependence. But we did see at the top that there was a reduction in drag. But more importantly, we found or as importantly, we found that there was an increase in pressure or a concern about increase in pressure just around these regions which correspond to the corner. So that influenced our recommendations on the curtain wall pressure. So those are three examples of some projects in China where there was a lot of effort put in the design and subsequent testing program in order to define vortex shedding and its influence on the structural loads and structural responses, all to good effect, because they're all viable projects, as you've heard throughout this Congress. So moving on to wind climate and some of the things that we're thinking about at RWDI, when we do wind tunnel tests, there's a certain model of the atmosphere that I'll mention in some detail, but just looking at some of the different actual storms that we need to consider, in a large part of the world, our extreme winds, at least close to ground, are controlled by thunderstorms. We have larger scale systems, some low pressure ridges or cyclones, sort of winter cyclones. In tropical areas such as Shanghai, we have typhoons, hurricanes in the North American lexicon. And then also sort of a driver, at least in the mid-latitudes, where I come from in Canada, we get into winter storms. So that's supposed to be a movie. I'm not sure if we can start that up. But anyway, this is a nor'easter. Those of you that from New York will certainly remember this nor'easter from January 2011. So when we look at the different storms, we can think in terms of different scales, different scale of wind effects. So if we're sort of defining scales, we tend to think of lengths. Down at this end, we have turbulence. Slightly bigger than turbulence is sort of microstorms or microbursts associated with thunderstorms and tornadoes. And then a little bit larger in scale, diurnal wind effects. And this is an example of a sea breeze effect, actually a land breeze effect for this particular one that we studied for a project in the Middle East. And then into the bigger scales, we get into tropical storms, weather fronts, and then very, very long waves, so sort of global scale events. But if we think about all of these, this scale is sort of weather. This scale is what we try to simulate in our experiments, in our wind tunnel. So we're very established and good methods at modeling atmospheric turbulence. We're working, this is sort of a research area at the moment, but we're working towards understanding how to model thunderstorms and understand their effect on supertall buildings. But if we look at the different profiles associated with those, these are sort of notional profiles, and we have our existing model, which is a standard boundary layer assumption. If we look at an extratropical synoptic from an actual set of work that we've done, matches that quite well. Looking at hurricanes, again, a little bit flatter. But the interesting one is where we get into thunderstorms, where we have that sort of low-level jet. So existing practice is that we model the standard model that I showed there with an atmospheric boundary layer, analyze the airport data for wind speed and directionality, and we come up with a wind climate, something like that. And then we bring that into our wind tunnel data, or map that onto the wind tunnel data to make some predictions. And in our discussions in the wind engineering group a couple of days ago, we talked a lot and debated about the merits of the different directionality methods, but certainly one, I think we would all agree that non-directional, which is to say that the design wind speed can come from any direction, such as what I've indicated there, results in something that's quite conservative. So beyond that, if we look at sort of uncertainty in those profiles, so I showed the different profiles associated with different storms, and the methods that have developed are certainly quite well established for buildings. I've put 500 meters here, some would say 300 meters, but certainly for the building heights that we are contemplating today, I think it's worthwhile to try to get an understanding of what the actual profile is for the particular region that we're working in. And there's a few different ways that we can do that. Weather balloon data, the real drawback on that is that weather balloons are not released in strong winds. So it doesn't actually give us any data for the design event, or something that may look like a design event. Radar data, which shows some promise, but it's only possible where the radar sort of sweeps, or the measurements from two stations overlap. A third way to do it is through direct measurement, but again, that's quite rare and in sort of the research realm, and it's only a few universities that I'm aware of that actually have the capability to measure profiles. But finally, the tool that we've started to use at RWDI is called weather research forecasting, and it's a model, it's a numerical model that's used by weather people in terms of forecasting, but we applied in another way. We applied in a hindcast mode to try to understand past storms and understand the nature of the wind profile at a particular location. So for winds that are typical in terms of driving the strong events, we want to understand what those profiles are. So Wharf models flows in the atmosphere at various scales, and the modeling is conducted with along with the hourly meteorological measurements. And so we work from a sort of a global scale of data that's publicly available at 1 degree. In the United States or North America, you can usually get a little bit higher resolution, which improves the accuracy. But nonetheless, it's working at sort of a global scale. Now, the drawback then is that they're nominal mean values, so it doesn't give us a lot of information on turbulence. In fact, no reliable information on turbulence. So that's one of the open questions that we have for certain types of storms, such as thunderstorms, for example. Just a little bit of evidence towards the balloon data. This is some analysis, again, for a project in the Middle East that we were involved with. And what I'm showing here is the balloon was released here, the balloon was released here, but it was too strong a wind to release it there, so it didn't give us any information. But we were able to use the balloon data to sort of validate or get a little bit of confidence in our Wharf modeling. And so you can see here that we did model, well, not exactly following the surface data. It gave some level of confidence in the technique. And more than that, it actually gave us some data on the peak event in that particular day. So the Wharf model, I'm just running a little bit out of time, but we're short on time. But the Wharf model, again, works from different scales. So we take data at a global model, and then we start to dial in to particular locations. So we've done that for different cities here in China, Beijing. We've worked on Hong Kong, Shenzhen area, and then finally around Shanghai. And the area extends out to include a fairly large area around Shanghai, including Suzhou and some of the other so-called Tier 2 cities that we heard about this morning. But gradually working and refining the grid, then we can get some information at a scale where we can start to make some analysis. So again, going back to the example from Saudi Arabia, the Middle East, we looked at a particular storm, and this was the maximum storm in one of the 10 years that we studied in a lot of detail with Wharf. And so again, this is the maximum wind speed measured at 10 meters in a particular year. And if we look at the evolution of that storm over a day, then we see that we get quite a significant variation from the standard assumptions that we use in the wind tunnel. And in fact, if we were to plot or extrapolate up from 10 meters with our standard assumption, you can see that we get quite a significant increase in the wind speed at height than what the WRF model predicted. And so therefore, you're getting quite a conservative result. Even though we don't know all the details about the turbulence, I think it's obvious to say that we have some conservatism, at least at 600 meters and above. So finally, I'll close just with a few comments on energy modeling, and this is work that was done by my partner Duncan Phillips. And I'm certainly not an expert in this area, but I'll just offer a few comments on his behalf on the sorts of things that he's starting to think about with respect to energy demand and specific to natural ventilation and its relationship with stack effect and some of the improved tools that we have to get meteorological data as input. So Duncan's been working and sort of running some generic models both at ground level and at 600 meters, and just to give some of the input parameters for a typical office space. But what he found in general is that in the sort of more temperate, and this is for a very hot climate, I should have mentioned that, it's a Middle East climate again, but for some of the more temperate times of years, so in the winter and perhaps early spring, late fall, then we're starting to see some good benefits from energy consumption point of view by looking at natural ventilation. And one more thing that he included in this is that he did find some differences in just standard atmospheric data assumptions that go into energy modeling versus what we were able to extract from the Wharf modeling, the WRF modeling. So again, that was a level of precision that he was able to add in. And while it didn't change the overall conclusion, it may have some effect on a particular design. But when we got into the very hot times of year in that particular climate, it didn't make any difference, because if you were to open the window, you would just, it would be very uncomfortable, put it that way. So just to end with a few comments here, first on the natural ventilation, that the analysis showed that there is some benefit of natural ventilation on cooling loads in the more temperate months in hot climates. So sort of confirming some of the notional conclusions that people have been arriving at. But one thing that he's starting to explore in a little bit more detail is how to retain control of stack effect when you have operable windows in a tall building. Because if you introduce opening windows into a tall building, and of course the human factor, then one quickly overcomes any of the gains that one gets from natural ventilation because of stack effect. And then just finally to conclude here, summarize a few things that I've talked about. Some opportunities for wind engineering that we can apply to projects, and we'll probably hear a little bit more throughout the session, and applied meteorology. One, we can certainly reduce the structural demand through building shape and considering the flow of wind in a positive way. Second, we can again reduce that structural demand through refined analysis of the meteorological data, and that certainly has a greater impact for some of the mega tall buildings that were being contemplated today. And then finally, just to summarize again the comment on natural ventilation, that there are opportunities for modeling and analysis of natural ventilation and reduced energy demand, both with the meteorological tools that I mentioned, but also some of the pressure data or other data that we derive from our wind engineering studies. With that, I thank you very much.
Yeah.